Sometimes when we're teaching class, we're so eager to introduce a very important fundamental that we real quickly say what are the underlying features, the underlying uh, restrictions, or I hate to use the word assumptions, but the underlying modeling characteristics that we use. That's a better word choice. The better modeling characteristics we choose to model our situation with. We say that real quick and then just jump right ahead. So I wanted to devote one video to describing and giving some examples of what is steady state, steady flow. What does that really mean? And it's such an important concept because so many of us engineers, both in when you look at the large proportion of coming up homework problems that you will have tend to be steady state, steady flow. A few others that are slightly different. And then in engineering practice, a large proportion of our open system problems and projects are associated with steady state, steady flow conditions. So I want to spend just a little bit of time talking about what does steady state, steady flow mean in the first place. So here we go. I hope that this gives you some ideas of when we plop down the word and when I show solutions, I say steady state, steady flow, and then boom, I move on to that. I hope that you'll have maybe a better physical feel for what the acronym SSSF really means. So let's see, we've looked at the continuity equation. So this is chapter 1, set 1 of my videos. We have drawn a sort of a cloud as an open system and recognize it's an open system because we have a number of mass flows into and out of the open system. And so we wrote down the continuity equation in general. And then we say, well, what about steady flow? What if all these m dot n's, they're all staying same in time, same in breakfast time as it is in lunch. And same for these outflows. They're all, if this particular flow is 5 gallons per minute, it's always 5 gallons per minute. And so that's what entitled us to strike out the left-hand side, the time rate of change of the control volume or open systems mass, that becomes 0. So we've got m dot n equals m dot e. So that's a statement of steady flow. The inflows exactly balance the outflows. So we've got steady flow defined, and I think you've got a good feel for it. Now let's work on steady state. Okay, so reminder, what does steady mean? Steady means nothing is changing in time. Nothing's changing in time. So in other words, everything that we've got, our mathematical model of our system is the same at breakfast time as it is at lunchtime. Nothing is changing in time. And so I've labeled my states. So for this particular sketch here, I've added a Q dot in and a W dot out. Oh, no, I didn't mention this yet. This might be the first occurrence for open systems. And notice here, I'm not saying W out. I'm saying W dot out. It's all about the dots. And so this is the rate at which work is being done. Q dot in, this is the rate at which heat is being added. It's not just heat added. It's not just kilojoules. It's kilojoules per second. That's kilowatts. Okay. W dot out is not just kilojoules. It's kilojoules per second. It's kilowatts. All right. I got off track a little bit, but that's important to describe. Okay. So I've got all these inflows and outflows, and I've labeled the states 1, 2, 3, all the way to 99. And I've labeled the outflows A, B, C, all the way to Z. And so I've already convinced you the mass flow rates for steady flow, they've all got to be constant values. Okay. Now let's see the states. Now let's look at the states 1, 2, 3, et cetera, et cetera. They've all got to be constant values. In other words, the pressure at state 1 is not changing. Temperature at 1, not changing. Pressure at Z, not changing. Temperature at Z, not changing in time. Same pressure and temperature at breakfast time as it is at lunchtime. Okay. Similarly, heat transfer rate, this Q dot in, the rate at which heat is being transferred, let's say 5 kilowatts. Okay. It's 5 kilowatts all the time. It's constant. It's a constant value. 5 kilowatts. And then, of course, the same thing for output power. It's steady. It's not changing in time. So I hope it's as simple as that. That's what steady state is. The states and the flow rates, they're all constant in time. So it's as simple as that. Now you got it. I declare you an expert in steady state, steady flow. Let's look at some examples. I'm SSSF, open system model. SSSF, steady state, steady flow. Well, here's a classic centrifugal pump. We've got one inlet and one outlet. It's a steel pump. This casing is steel. The pump cannot get fatter or skinnier as time goes by. So it's a fixed volume there. And so the inlet flow exactly equals the outlet flow. And for it to be steady state, steady flow, the inlet pressure is constant. The outlet pressure is a constant value. The inlet temperature is some constant value. And the outlet temperature is some constant value, and on and on. Classic example of steady state, steady flow, real world, open system process. One inlet, one outlet. All right, here's another one inlet and one outlet, steady state, steady flow example. It's a steam turbine. This is a cutaway view of it. We've got steam flowing into the inlet of the steam turbine. It's expanding against this rotor, against the blades of the different stages of the steam turbine. It's turning the rotor, and the rotor is therefore providing an output torque and speed, all at a constant value for the shaft going to an electric generator. So I've shown W dot out, and here's the discharge, which also the mass flow is constant, and the pressure and temperature at the outflow is a constant value in time. Classic steam turbine. Now, this is a real honest to goodness what we call open feed water heater from a power plant, which has 2 inlets and 1 outlet. And so without giving you the details about the purpose of this vessel and things like that, do recognize that I've got 2 inlets. I've got a condensate return from some place in the power plant. So this is water coming in, and our objective is to heat the water, and we heat it with steam coming in. And so those 2 streams mix together in a steady manner. And so there's only 1 outlet that I've called hot feed water, and it goes off to a feed water pump where it's pumped up into the boiler. But anyway, do recognize that this is an example of an open system, steady state, steady flow. Things aren't changing with time, with 2 inlets and 1 outlet. Simple as that. Example 4. This is a gas turbine engine, and we call it a turbojet because notice there's no shaft coming out of this particular engine. So this is a classic aircraft engine where we've got, it's a number of pieces of equipment. This is called the compressor section. This is called the turbine section. And in here, there's a combustion chamber in here. And for my thermodynamic model, I'm saying I'm adding heat at a certain rate, Q dot in so many kilowatts or megawatts coming in to heat the air that's coming in. And so do you see that our thermodynamic model is going to be 1 inlet and 1 outlet, steady state, steady flow, open system. A 5th example, also a stationary. It's a gas turbine engine. This is a stationary gas turbine engine, and its purpose is to drive an electric generator. And so for this case, we've got the same compressor section. We have a turbine section. We're modeling the combustion chamber as heat added, Q dot in. And so notice here, we've got air coming into the compressor section. We've got air leaving the turbine section, 1 inlet, 1 outlet. And in this case, a shaft is turning at a constant speed and torque and driving an electric power generator, W dot out. Classic 1 inlet, 1 outlet, steady state, steady flow, open system. Okay, no number crunching on this one. No formulas provided. It's all now. It's up in your head, I hope. So we have defined steady state, steady flow. That I use the acronym SSSF for open system models. So it's a special type of model, right? The flows and states are constant in time. And you might think, how can I remember this? It's the same operation. The equipment is operating exactly the same at breakfast time as it is at lunchtime. It's time independent. So that gives you a better physical feel for what is steady state, steady flow. Coming up next is going to be a very involved but extraordinarily important concept where I'm going to try to summarize the textbook where it goes through and it derives, and I'm going to sort of jump to the bottom line of the statement of the first law of thermodynamics for any open system. So it can become very complex, but you need to maybe not necessarily master the general statement of the first law for an open system, not necessarily totally get it into your head, but at least have a physical feel for what it's all about. What are the terms all about? What are the variables all about? So I'm going to try to help give you a better working understanding of the first law of thermodynamics for an open system. Okay, hope that helps, and hope that you'll join me for the next video.